Okay, so this is a follow-up to the warm-up activity that we did on Monday. So let's look at each one of these problems. The first one says a mixture of the gases, nitrogen, oxygen, and helium has a total pressure of 760 millimeters of mercury. If the partial pressure of nitrogen is 90 millimeters of mercury and of oxygen is 270 millimeters of mercury, what is the partial pressure of helium? So because this is a partial pressure question, and it has to do with the total pressure, and we're not given anything about moles or grams, I know that the formula that I'm going to use for this particular equation is P total is equal to the sum of all of the gases, the partial pressures of all the gases. So the sum of the partial pressure of nitrogen gas, the partial pressure of oxygen gas, and the partial pressure of helium. In this problem, we want to find the partial pressure of helium. We are given P total. We are given the partial pressure of nitrogen and the partial pressure of oxygen. So this is simply going to be the rearrangement of this equation. So the partial pressure of helium then is going to equal P total minus the partial pressure of nitrogen minus the partial pressure of oxygen. And so we can just plug in all of those values. So you'll have 760 millimeters of mercury minus 90 millimeters of mercury minus 270 millimeters of mercury. And you put this in your calculator and you'll see that the partial pressure of helium is 400 millimeters of mercury. Now, if you wanted to say convert this to ATMs, then you would use the conversion factor for every 760 millimeters of mercury. There's 1 ATM. And so that would give you 0.526 ATMs. Okay, so let's look at this next problem. This next problem says calculate the volume of a 3.50 mole sample of carbon dioxide at 30 degrees Celsius in 0.9 atmospheres. So I look at this problem. I want to find volume. I'm given moles. I'm given a temperature. And I'm given atmospheres. So I know that from the ideal gas law, pressure times volume is equal to nRT. I can rearrange this equation to solve for volume. So volume is going to equal nRT over P. I have N, R is a constant. I have T. I need to convert this T into kelvins, and then I have P for pressure. So let's look at the Kelvin temperature for 30 degrees Celsius. So we have 30.0 degrees Celsius plus 273.15. So this is equal to 303.15 Kelvin. So we can just plug everything in. So you have 3.5 moles, 0.08206. This is liters times atmospheres over moles times Kelvin times temperature, so 303.15 Kelvin, all divided by 0.9 atmospheres. All right, Our moles cancel out, our kelvins cancel out, our atmospheres cancel out. We're left with liters. So 3.50 times the ideal gas law divided by 0.9. All right, so the volume of the sample then is 96.74 liters. Now you can kind of even check yourself a little bit to see if this makes sense. You know that if you're using the ideal gas law, the molar volume at STP is going to be, or the volume at STP is going to be 22.4 liters. Now you can see that you have a higher temperature than that at STP, right? The pressure is about the same, and then you have more than just 1 mole. So you would expect this to be, a couple times higher than 22.4. And in fact, it is of a magnitude that you would expect. So it's nice to have a sensibility about what value your calculation should actually be. Okay, so let's look at this next problem. It says the molecular weight of a gas is blank grams per mole. If 3.5 grams of the gas occupies 2.1 liters at STP. So we're given information that we can use in the ideal gas law, right? We're given grams, and we want to find the molecular weight. So here's the options that we have for this. So you know that from the density formula, mass over volume is equal to the molar mass times the pressure divided by R times T. So you can rearrange this equation here such that molar mass is equal to mass times R times T divided by volume times P. You have mass, you have R, you have T, you have the volume, and you have P. So it's just a matter of plugging in all of these variables. Now, an alternative way to solve this problem, and had I not just taught you guys this chapter, I would have solved it this other way because I can't remember this formula, on just like a regular day. I would have, so from the ideal gas law, you have PV is equal to nRT. If you rearrange that equation, N is equal to PV, right, divided by RT. I would solve for the number of moles and then just divide that number of moles by the grams given. So that's another way you can approach this problem. But since this chapter provides you with this nifty formula, you can just use the formula. However it makes the most sense to you, do it that way. Okay, so this would be 3.5 grams times R, which is 0.08206 liters times atmospheres over moles times kelvins, times T, which is 273.15 Kelvin at STP, divided by volume, which is 2.1 liters, times 1 atmosphere. So our liters cancel out, our atmospheres cancel out, our kelvins cancel out. We're left with grams per mole, which is what we want for molar mass. And then you can put this in your calculator, 3.5 times R. So the molar mass here is going to equal 37.36 grams per mole. And I'm going to actually look on the periodic table and see if I can identify this particular mass, molar mass, the element that corresponds to this molar mass. And if I look on the periodic table, if I divide this by 2, 37, so I looked on the periodic table, I didn't see anything that was about 37 that could be a gas. And so then I thought, well, let me divide this by 2, and if I divide it by 2, then I get 18.8. 18.7. So it could be possibly fluorine gas, because that can be a gas that would correspond to this molecular weight. Alright, so let's look at this stoichiometry one. So automobile airbags use the decomposition of sodium azide as their source of gas for rapid inflation. So you have 2 moles of sodium azide decomposing to solid sodium plus nitrogen gas. So we want to know the mass of sodium azide required to provide 0.265 milliliters of nitrogen gas at 22 degrees Celsius in 1.1 atmospheres. So what we're going to do is we want to find something about, we're given information about about the nitrogen gas. So we want to find out moles of nitrogen gas, and we can use moles of nitrogen gas in this equation to find moles of sodium azide, and then we can use the molar mass of sodium azide to find the the grams. So let's do this. Let's write the ideal gas law. PV is equal to nRT. We want to rearrange this to solve for N, so N is equal to PV divided by RT. We're given P, we have V, we have to convert V into liters. We have R, we have T, we have to convert T into Kelvin. Alright, so we have 1.1 atmospheres times, I'm going to convert this into liters. It's going to be a really small number of liters. So it's going to be 2.65 times 10 to the minus 5 liters. And then times R, 0.08206 liters atmospheres or moles times Kelvin. 22 plus 273 will give us our temperature in Kelvin. Our Kelvin temperature is 295.15. So our atmospheres and liters cancel out, our kelvins cancel out. This is going to be probably a small number of moles, yep. 1.20 times 10 to the minus 6 moles of nitrogen. Okay, so now we're going to do the stoichiometry. So if we have 1.20 times 10 to the minus 6 moles of N2, from this chemical reaction right here, for every 3 moles of N2, there are 2 moles of sodium azide. And then we want grams ultimately, right, of the sodium azide. So for every 1 mole of sodium azide, I'm going to calculate the molar mass here. So 22.989770 plus 14.0067 times 3. So 65.0099 grams. All right. Let's put this in the calculator. And it's probably going to be some small mass because the volume to begin with was really small. All right, so the number of grams I get is 5.20 times 10 to the minus 5 grams of sodium azide. All right, let's look at the next problem. So the next problem says a sample of gas, it's 5 moles, at 1 atm is expanded at constant temperature from 10 liters to 15 liters. We want to find the final pressure in atmospheres. So we have an initial volume, a final volume, an initial pressure, and a final pressure. So this means we can use one of those simple gas laws. We can use P1, V1 is equal to P2, V2. And remember that, remember this formula, it can help you to remember that P is, right, inversely proportional to volume. So as volume decreases, pressure increases. All right, so let's rearrange this equation. We're going to solve for P2. So P2 is equal to P1 V1 over V2. And so we can just simply plug in all of these values. We have 1 atm times 10 liters divided by 15 liters. So 10 divided by 15, P2 is equal to 0.667 atm. And if you're doing sig figs, you would need just 2 sig figs, so it would be 0.67. All right, so let's look at this next one. A mixture of xenon, krypton, and argon has a total pressure of 6.69 atmospheres. Okay, so we have P total. What is the mole fraction of krypton if the partial pressures of xenon and argon are 1.92 atmospheres and 2.75 atmospheres, respectively? So let's look at a couple of things. So we want to find the mole fraction of krypton. So let me write that equation. So the mole fraction of krypton is going to be equal to the number of moles of krypton over N total, or we can think of the moles of krypton, or the mole fraction of krypton, as being equal to the partial pressure of krypton divided by P total. So those are our two options for finding a mole fraction. And so if you compare each one of these options, you'll see that it's going to be difficult to get all of the information about moles. We're not given anything about grams, we're not given anything about moles. So this is kind of, this is going to be hard, but if we look at this other option, if we find the partial pressure of krypton, and we know the total pressure, then we can find the mole fraction. So we have the total, P total, and then we have the partial pressures of xenon and argon. So P total is equal to the partial pressure of xenon plus the partial pressure of krypton plus the partial pressure of argon. We can solve for the partial pressure of krypton. P krypton is equal to P total minus the partial pressure of xenon minus the partial pressure of argon. So this is going to equal 6.69 ATM minus 1.92 ATM minus 2.75 ATM. Okay, let me put this in the calculator. So the partial pressure of krypton then is going to be 2.02 atmospheres. So now we have all of the information to find the mole fraction. So the mole fraction then is equal to 2.02 atmospheres. This is the partial pressure of krypton divided by P total. P total is 6.69 atmospheres. So this is going to be equal to 0.302. And remember, fractions don't actually have units, so there's no units here. So the mole fraction of krypton is 0.302. And if we're doing sig figs, yes, we have the correct number of sig figs. Let's look at the next problem. So in this problem, you're asked to find the root mean square speed of N2, nitrogen gas, at 33.5 degrees Celsius. So the root mean square formula says the root mean squared is equal to the square root of 3 RT divided by the molar mass of the compound of interest. So you have 3 and you have R, those are givens. T, we need T. And oh, remember that when you're doing this, the R that you need to use, it has to be the R that's in joules. And since it's joules per kilogram times moles, that your molar mass of nitrogen gas needs to be converted into kilograms. So let's write all of those things out. So R for this is 8.314 joules per mole times Kelvin. T is going to be 33.5 plus 273.15. It's going to be 306.65 Kelvin. And then the molar mass of nitrogen. So nitrogen is 14.01. So 14.01 times 2 is 28.02. We're going to have to divide this by 1,000 to get it into kilograms. So remember, grams are a smaller unit than kilograms, so there has to be less kilograms than grams. So 0.02802 kilograms per mole. Now we can just plug all of these variables into this equation. So we have the root mean squared is equal to the square root of 3 times R times the temperature, which is 306.65 Kelvin, divided by the molar mass, which is 0.02802 kilograms per mole. Let's put this in the calculator. Alright, so the root mean squared then is 522.46 meters per second. Okay, so let's look at the next one. It says, of the following gases, and I forgot to write those, but I think we said helium and krypton, maybe we said helium and argon. It doesn't matter which gases. The exact gases that I said in class are sort of irrelevant. Knowing how to solve this problem is relevant though. So we're comparing two gases, and that's what you might be asked to do. So we're going to compare the rate of effusion of helium and krypton. So remember from the equation that we just wrote that the root mean squared velocity is equal to the square root of 3RT over the molar mass. So as the molar mass gets smaller, with a small molar mass, the velocity is going to be greater. And with a large molar mass, the velocity will be less. If you have a higher velocity, those particles are going to be moving faster. They're going to have more collisions. If they have more collisions, they're going to effuse faster, right? And so whichever one of these has the smaller molar mass is going to be have the greatest rate of effusion at a given temperature. And you guys should know that helium is the second element on the periodic table, so it's going to have a lower molar mass than krypton. We don't even need to look at the periodic table to know that. So helium will have the greatest rate of effusion at any particular temperature. Alright, so let's look at the last problem. It says a fixed amount of gas at 25 degrees Celsius occupies a volume of 8.66 liters when the pressure is 629 torr. We want to calculate the volume in liters that this gas will occupy when the temperature is increased to 112 degrees while maintaining the pressure at 629 torr. So this is telling us that pressure is constant. However, we have a change in volume. We want to find a change in volume, and we have a change in temperature, right? So if we think about those simple gas laws, we have a formula that relates volume and temperature under two sets of conditions. It's V1 over T1 is equal to V2 over T2. Now remember though that we only said that this was valid for degrees, well, not degrees Kelvin, for Kelvin and not degrees Celsius. So we need to convert each one of these temperatures to Kelvin. We're going to be finding V2, so we can just rearrange this equation too while we're at it. So V2 is going to equal V1 times T2 over T1. So we have 8.66 liters times T2 is 112 degrees Celsius. We're going to add 273.15 to that. That's 385.15 divided by 25 plus 273.15. That's the second temperature, is 25 degrees Celsius. That's 298.15 Kelvin. Kelvins cancel out. We're going to be left just with volume. 8.66 times 385.15, all divided by 298.15. It's going to give us 11.19 liters. Now let's see if this makes sense. Okay, so volume and temperature are proportional. So if if temperature has decreased, volume's going to decrease. If temperature increases, volume's going to increase. So we go from a low temperature to a high temperature, so we expect for volume to increase. Volume goes from 8.66 liters to 11.19 liters. So our sensibility, about this question is helping us, determine whether or not this answer is reasonable, and in fact it is.